All right, in this video, we're going to look at the second part of example 5.5. In the first part, the object in the problem was not moving. That is not the case in this problem. In this problem, it says a man is pushing a 150 kilogram desk across the floor. The frictional coefficients between the desk and the floor are, and then they give us those. If the desk is already moving, how much force must the object exert to keep the desk accelerating at 0.3 meters per second squared? Okay, so let's kind of analyze what this problem looks like here. First of all, the object is not still, the object is accelerating. So what does that tell us? Well, if the object is accelerating, that means there has to be a net force in one direction or another, okay? We know the mass, we know the acceleration, and we also know both the coefficients of static and kinetic friction. So whenever we start a problem like this, again, the first thing that we need to do is we need to draw a diagram that's going to illustrate our forces here. So here's my desk, and the guy is pushing this direction on the desk. I don't know exactly what kind of position he's in there, but anyway, he's pushing on the desk that direction. Okay, so he is pushing on the desk this way with some sort of force. We know that because it's, again, he's not pushing this on a sheet of ice or something. We know that friction is going to be pushing against his motion. We know that gravity is going to be acting on this, so the weight of the object is going to be pulling it down. But it doesn't say that the object is accelerating upwards because he's pushing this way. So that means we also have a normal force that's going to be moving that direction. Is that all the forces? Well, yeah, as far as I know, that's all the forces that we have acting on this here. Okay, so let's analyze this. As I said a minute ago, we know that if the object is accelerating, there has to be some sort of a net force going on. So I'm just going to say, okay, that net force has to be equal to the mass times the acceleration. That's what we know from Newton's second law. Okay? Now, if I say net force, what am I really talking about? Well, if you're familiar with the word net, what that means is that if you have a job, for example, and then you go to work and you earn a certain amount of money, but then the government takes out part of it in taxes, then what you bring home is your net pay. So it's the amount you earned minus the part that the government took. So that's your net pay. Your gross pay is what you earned. Your net pay is what you're actually taking home. So here, the net force is the overall force that you actually get to take home with you. It's what's ultimately causing the acceleration for this desk. So according to the diagram that we've drawn, what's going to be the case here? Well, I know that the motion of the desk is this direction because the guy is pushing on it. Okay, so I know that the motion goes this way. So I know that this force is going to be overcoming the force of friction, which is this way. So the net force then is going to be the force that the guy is applying minus the frictional force. That's going to be my net force, okay? And so therefore that's going to equal mass times acceleration. Well, what is this frictional force? Well, I know that the frictional force is the coefficient of friction times the normal force. Do I know the normal force? No, I don't know the normal force yet. So basically what I need to do is, in order to figure out what this frictional force is, the first thing I've got to do is calculate what the normal force is. So the normal force is going to be equal to the mass times gravity. And so the normal force is going to be equal to 150 kilograms times 9.8 meters per second squared. And so that means my normal force is going to be equal to 1,500 newtons, two significant figures. Okay, so there's my normal force. Can I then calculate the frictional force? Yeah, I can calculate the frictional force now. So my frictional force is going to be equal to mu times the normal force. Now, do I want the coefficient of static friction or the coefficient of kinetic friction? Is the object moving? It is moving. He already has it moving because we've been told that it's accelerating. So he's already overcome the static friction. So now he just has to overcome kinetic friction. So my frictional force then is going to be the coefficient of kinetic friction, which is 0.35, times the normal force, which is 1500 newtons. So therefore, my frictional force, if I multiply those two numbers together, is going to be 530 newtons. Again, just two significant figures because that's what each one of those had. Okay, so therefore, the force that he's applying, that's what I'm trying to figure out. I have to subtract off the frictional force, which I just figured out was 530 newtons. It's going to be equal to the mass times the acceleration. Well, I know that the mass is 150 kilograms, and I know that it's accelerating at 0.30 meters per second squared. I never do quite leave enough room for that, do I? Okay, so that's going to be equal to that. So then if I multiply these two together, and then I add the 530 newtons to that, I end up with, if I take 150 times 0.3, that's going to give me 45 newtons on this side, equals F times or minus 530 newtons. And then if I add 530 newtons to both sides of the equation, that's going to give me 580 newtons. Now be careful with significant figures here. They both have two significant figures, but I'm adding and subtracting this time. And this last significant figure is in the tens place, and this one is in the ones or the units place. So that means in my answer, the significant figure is going to have to be in the tens place and not in the units place. Okay, so let's kind of go back and summarize what we've done here. I know that the object is moving, so I know that it had to have a net force on it. That net force is the man pushing, and I'm going to subtract off the frictional force. And that net force then is equal to the mass times the acceleration. So he uses this equation, and that's where it came from. So you probably will want to write this equation down on your card for your test so that you've got that, but you need to remember what exactly that all means, okay? So then I was able to calculate the frictional force because I knew the mass, so I could calculate the normal force. Then I could use the normal force to calculate the frictional force. And then because I knew the mass and the acceleration, I could plug that in on the other side. So that gives me this net force that he is actually applying. So that is an example of a problem where an object is accelerating. And then if you want to see an example where the object is at constant velocity, then you'll need to find the third part of this video.